Hello, everybody. It's Matteo Buzzegoli from Florence University. And first, I want to thank the organizer for having me here and for all the discussion we are having here. Thank you. And in this talk, I will propose a new observable to detect local parity violation in relativistic heavy ion collisions. As you all know, relativistic heavy ion collisions allow to look for quantum effects on fluids, among others. For instance, we can detect quantum effects on hydrodynamics induced by thermal vorticity by observing the polarization of emitted hadrons from the quark gluon plasma. And what would be the topics of this talk is the local parity violation in QCD that are currently being investigated in relativistic heavy ion collision through the chiral magnetic effect, as has been reviewed in the previous talk by Xinfeng Liao. But let me remind you just some points. So we have that in the QCD vacuum, we can have non-trivial topological configuration of gluon fields, and these can be transferred to the axial current of fermions through the axial anomaly. And therefore, the quark gluon plasma is generated with an imbalance between right and left-handed quarks. And this imbalance is described in hydrodynamics with an axial chemical potential mu A. And you can look for the presence of this axial chemical potential by looking at the charge separation of in the hadron spectrum along the magnetic field. And this will be the signature of the presence of this axial chemical potential. This is how currently this axial chemical potential is being investigated. But now I'm going to propose you another method which does not rely on the chiral magnetic effect. This idea has been proposed on this paper recently uploaded in the archives by Francesco, me, Andrea, and Georgi. And what I'm going to show you now is the presence of an axial imbalance in the quark gluon plasma induces a term in the polarization of the hadron of spin 1/2 emitted by the quark gluon plasma. And this polarization is shown here for a special case. And the polarization in the rest frame of the particle is proportional to zeta A, which is the ratio between the axial chemical potential and the temperature. So if we have this polarization, this also means that axial imbalance also induces a term in the helicity of the particles, which is also proportional to the axial chemical potential. And we could observe this in the helicity independently of the magnetic field. So this helicity induced by axial imbalance is a parity breaking term contribution, and because it is a local parity violation term in the helicity, it has a peculiar features in the azimuthal angle dependence of the helicity. For instance, as it is shown on the right, this is the helicity induced by thermal vorticity, which preserves parity. That is, it doesn't change signs under a parity transformation. Instead, on the left, you have an example of the contribution from axial imbalance from a single event. And notice how the sign does not change under parity transformation. So we can try and detect these effects in the observed helicity. And more details later. So the mean spin vector of a spin 1/2 hadron emitted by the quark gluon plasma has two contributions. one terms from the thermal vorticity given by this formula, which has been discussed at length in this workshop. And what I'm going to show you in a moment, that the axial imbalance also induces this additional contribution. And these two formula have several similarities. They are both integrals over the freeze-out hypersurface, and they also depend on these thermal fields. One is the thermal vorticity, and one is the axial imbalance. But they are both thermal hydrodynamics fields that fluctuates on event-by-event basis, but the thermal vorticity does not violate parity and fluctuates event by event with a positive average, whereas zeta A describes local parity violation, and event by event it fluctuates around 0 with vanishing average over multiple events. And therefore, in the previous observation measurements of polarization, which requires an average over multiple events, this additional contribution from axial imbalance is averaged out, and you don't see this effect on previous measurements. But what we can observe is the effects of the square of this zeta A, which is non-vanishing even if it is averaged over multiple events. But more on this later. Let me, for now, just show you how to derive this formula. So we're going to use this formula for spin-on hadron. This gives the mean spin vector, and requires the Wigner function, which for a Dirac field is given by this formula, and which we have to trace Wigner operator with a density matrix. Therefore, we first have to provide a density matrix for the system, then we can evaluate the Wigner function and then the spin vector. And for a relativistic fluid, which at some time is believed to have achieved local thermodynamic equilibrium, a powerful approach is the Zuberow method of the stationary non-equilibrium density operator. And this approach is especially well suited for the physics of relativistic nuclear collisions, where the system supposedly achieves local thermodynamic equilibrium at some finite early time to form a core-gluon plasma phase, which lives in a finite space-time region before breaking up at some 3D hypersurface, which we call the freeze-out hypersurface. And for a system which is a local thermodynamic equilibrium, the density operator can be obtained by maximizing the entropy of the system with constraints on the energy density and the momentum density, and with charges density. And for instance, we know that the core-gluon plasma is generated with an axial imbalance. Therefore, we can maximize the entropy with an axial charge density. And the result is this density operator, where sigma is the hypersurface at local thermodynamic equilibrium, T is the symmetric stress energy tensor, beta is the inverse for temperature, zeta A is the ratio between the axial chemical potential and temperature, and JA is the axial current. But as it stands in this form, this operator is not suitable to compute the Wigner function and the spin vector, because as you clearly see, these are operators in terms of the effective hadronic fields. And for example, the fields for the lambda particle. Instead, this operator lives in the core-gluon plasma phase, where the stress energy tensor and the axial current are given in terms of the QCT degrees of freedom, which are quarks and gluons. Therefore, we have to move this operator from this hypersurface to the freeze-out hypersurface. And this can be done by means of the Gauss theorem. And the difference between these two hypersurface is just a volume integral over omega, which is the volume, the region of space between encompassed by these two hypersurfaces, and is the integral over the divergence of the previous integrand, and so it's given by those terms. And these volume integrals contains information about the dissipative terms of the evolution, and these are small compared to this leading term, because beta and zeta A are hydrodynamics fields. Therefore, they varies over a macroscopic length scale. Therefore, their derivatives is small compared to the microscopic scales. And then, because in hot QCD chiral symmetry is restored, the divergence of the axial current is small. Therefore, you can neglect these additional dissipative terms, and you can approximate the density operator, which used to calculate Wigner function spin vector, with the density operator at a local thermodynamic equilibrium, where sigma is the freeze-out hypersurface. The stress energy tensor can be given in terms of the effective hadronics fields. Okay, now we can use this operator to compute the Wigner function. We have to make this trace of the density operator with the Wigner operator, and we can take advantage of the fact that this beta field is an hydrodynamic field, therefore is a slowly varying field, which we can Taylor expand at the point x, where x is the same point where we want to evaluate the Wigner function. Therefore, you can replace to this beta this expression given by this leading term, which reproduces this term, which is the homogeneous thermodynamic equilibrium term. Then we can consider the derivatives terms. For instance, in this way, we reproduces the thermal vorticity. And then there are also additional terms that here we have not considered. But what will be the focus of this talk is this term of the axial current that we had here. But then these two additional operators, in addition to the total angular momentum, are a small correction. Therefore, we can use linear response theory to approximate the density operator. And therefore, this correction becomes linear, just the sum of these two operators. And we can, this way, evaluate the Wigner function. Therefore, we have a leading term, which is just the Wigner function at homogeneous thermodynamic equilibrium with temperature evaluated at the point x. And then we have this additional correction, which are linear on thermal vorticity and axial current. If we consider also the term from thermal vorticity, this would bring to the polarization loss thermal vorticity, the well-known formula, which is just an additional term to add to the polarization. Therefore, we have not considered this here, but here we consider the correction from the axial current, which is given by the integral of this correlator, which is the correlator between the Wigner function and the axial current. Notice that this thermal average is computed with the density operator of the homogeneous thermodynamic equilibrium. Therefore, we can just use usual thermal field theory techniques to evaluate all these quantities. But then this Wigner function is given in terms of the hadronics fields. Instead, the axial current is the color singlet axial current, and is composed by quarks and gluons. And therefore, we have to rewrite these in terms of the effective hadronic fields. And for any operator, we can decompose it in multiple particle states just by summing over the number of particles and on this hadronic species. And is given by the momentum integral of a creation and destruction operator weighted with some function. But what we are interested in is in the correlator between the Wigner function for a specific hadronic species, for instance, for the lambda particle, and this axial current. Therefore, this correlator selects among all these terms just the one of the same hadronic species of the Wigner function. And among all these terms, the predominant contribution is just the terms which contains just one creation and one destruction operator, which is highlighted in red in this formula. And in this case, for this term, this function is just the matrix element of the axial current evaluated between an ingoing and outgoing one particle states of these hadronic species. And since we are interested in spin 1/2 particles, one can show that this matrix element must have this form, where U is the Dirac spinor, and GA1 and GA2 are two form factors, which can be evaluated starting from this density matrix. Okay, therefore now we have all the elements to evaluate the Wigner function and to evaluate all this thermal expression value. The result is that the leading term is just the Wigner function at homogeneous thermodynamic equilibrium, and therefore it depends on the Fermi-Dirac distribution function with temperature at the point x. And then we have the linear response of axial current, which is given by this expression, which of course contains the two previous form factors from the axial current. Then we can plug the Wigner function inside the formula for the polarization, and we obtain this expression, and therefore this is the polarization induced by the axial imbalance. Then we have just to evaluate these traces, and we obtain these results. And for now, let's just focus on this blue part. Here, this is an integral over the freeze-out hypersurface with variables y. And all the y dependence is contained in this blue part. And notice that this integral is rapidly decaying when we over a microscopic length scale, meaning that when y is far from x, this integral is vanishing. So I can rewrite this blue part here, and also this integral involves the zeta A, which is an hydrodynamic fields, that therefore should varies on a longer length scale. Therefore, we can approximate this integral by replacing the value of zeta A with its value at the point x, and remove it from the sign of the integral. And the rest of the integrals can be made through the thanks to the Gauss theorem. And the result is, if the volume is large enough, this can be the result is a Dirac delta, and this integral is directed along t hat, which is just the time direction in the center of mass frame. Therefore, if you can use this approximation and replace this here, then we can simplify the expression by integrating, and eventually we obtain this formula that I've shown you before, where GH here is just the first form factor evaluated at zero momentum transfer, and is the axial charge of the baryon species. Then we can rewrite this formula in a more suggestive way, just by back boosting this polarization vector into the rest frame of the hadron. And the result is a polarization which is directed along the momentum of the particle P, where this momentum P here is the momentum of the particle in the rest frame of the core gluon plasma, and then is given by this. Then it has a factor which we have called F chi, which involves an integration over the freeze-out hypersurface and is proportional to zeta A. But if we have this polarization induced by axial imbalance, this also means that we have an helicity induced by axial imbalance, because we just have to project the polarization along the momentum of the particle, and therefore we find that the helicity induced by axial imbalance is just this function f chi. And we can write this, simplify this formula in a special case when zeta A is almost constant, and when the quantum effects on thermal distribution function are small, and we can approximate 1 minus the Fermi Dirac distribution with 1, then the numerator and denominator simplify, and the polarization is given simply by a factor which is just proportional to the to zeta A, and is divided by 2, and is proportional to the axial charge of the baryon species. Okay, this is the derivation. So what I've shown you is that the presence of an axial imbalance induces an helicity, which is linear on the axial chemical potential. Therefore, one can try to measure this term inside the helicity without the mediation of a magnetic field. But like for the search of the chiral magnetic effect, the problem in detecting zeta A is that if that it fluctuates on an event-by-event basis with zero average, and that's because it is a local parity violation. So what we can do is to look for a square effect which survives the average over multiple events. And since the helicity contribution from axial imbalance has peculiar features in the dependence of the azimuthal angle, because they are parity breaking terms, then we can take advantage of this fact. And what we propose is to search for the contribution of axial imbalance in the azimuthal angle dependence of helicity. Let me expand on this idea a little more. So consider the geometry of a typical nuclear collision. This is a sketch. And we see that the geometry of the collision has a parity symmetry, and also a symmetry on the rotation along the total angular momentum with angle pi. And these symmetries are also reflected in the shapes of the freeze-out hypersurface, and this means that quantities that depends on the momentum, such as the polarization and the helicity, are constrained by these symmetries. And just a reminder, the parity transformation in momentum space is just the change of sign of the space part of the momentum. And then the symmetry of the geometry is always there, even if there are parity violating phenomena. What changes is the symmetry of the density matrix. If we don't have an axial charge, the density matrix is also parity invariance. Therefore, the helicity must be a pseudo-scalar, meaning that when we make a parity transformation, it acquires signs. For example, the helicity induced by thermal vorticity is a pseudo-scalar. Instead, when we have local parity violation and we have axial charge, then the density matrix is no longer parity invariant, and helicity can acquire terms which are scalar under parity transformation. And one example is the helicity induced by axial balance that I've shown you before, And indeed, you can check that this f chi is scalar under parity transformation. Therefore, we can, in general, we can split the helicity in two contributions, one pseudo-scalar part and one scalar part, which is coming from local parity violation. And if one can detect the scalar part of helicity, then this will be the signature of local parity violation. So consider a particle submitted at mid-rapidity, meaning that its momentum along the beam direction is 0. Therefore, we can parameterize the momentum with a modulus of the transverse momentum, pt, and an azimuthal angle. Then you can split, you can write helicity as a single variable Fourier expansion in the azimuthal angle phi. And this form is constrained by rotational symmetry that is coming from the geometry. And then because we split in the pseudo-scalar and scalar part, they also have special reflection properties. Therefore, the pseudo-scalar and the scalar part Fourier expansion must have this expression, and this is a model independent. And so you can see the behavior of these two terms. For instance, the pseudo-scalar part behave in this way. For instance, we've chosen these values for the harmonics, just as an example. Instead, the scalar parts have this behavior, which is different. For instance, the sign of the helicity is maintained in both in the upper and the lower half plane of the figure. So what we expect is that if we have local parity violation, then the values of these harmonics of the scalar part of the helicity are different from 0. But from global parity conservation, the average over multiple momentum is vanishing. Therefore, to look for these effects, we have to square the helicity. And if we square the helicity with this Fourier expansion, and if we keep just the leading harmonics, we find this expression. And when we average over multiple events, even if the linear terms in the scalar part are vanishing, but the squared terms are different from 0. Therefore, by measurement of helicity square, one can detect such terms and identify local parity violation. For example, you see in the figure this helicity square averaged over multiple events. If there is no local parity violation, have this behavior. Instead, with local parity violation, these values is the function is moved up with a step function. Or it want to be a very simple way to see this is at looking at this helicity square at angle phi 0 or pi. And if you see that this function is different from 0, then this contribution can only come from the scalar part. Therefore, the detection of the helicity square, an unvanishing helicity square at angle 0 or pi, is an undeniable sign of local parity violation. In a similar way, we can, for instance, look at the helicity-helicity correlators. Therefore, the helicity between two hyperons, provided that they are emitted in the same event with a different angle. So the formula for the correlator is this one. But for instance, consider the the correlation coming from the pseudo scalar part of helicity, meaning without local parity violation, and consider the correlation between two particles at a large angle. For instance, a particle, the first particle emitted with angle phi, and the second particle emitted with angle phi plus pi. And you see that the two signs of the helicity are opposite. Instead, from the scalar part, which comes from the local parity violation, even if the fluctuation in a single event is either positive or negative, but the sign of the two particles are the same, therefore the correlator is positive. Therefore, for local parity violation, we expect positive correlation at large angles. And if we if we replace in this formula the Fourier expansion of in H1 and H2, and we keep just the first harmonics, then the formula is simplified in by this integral. And the result is a constant term coming from local parity violation and the terms that you expect without parity violation. And again, you see in red the correlator average at a vanishing value at 0. Instead, if you have terms given by local parity violation, the average of this correlator is non-vanishing. Therefore, a detection of such a non-vanishing average is again a signature of local parity violation. So, by summarizing, what I've shown you is that local parity violation in relativistic nuclear collisions can be detected by measuring polarization, for example, by looking at the helicity and the polarization of lambda hyperons. And we can search for parity breaking terms in the helicity by looking at its azimuthal dependence. And therefore, we propose to use spin as a probe of axial chemical potential. Thank you.
Yeah, thank you very much, Matteo. Very interesting talk. And oh, yeah, I see already a couple of questions. Masoud was first.
Hi.
Hi.
Thanks for the nice talk. I want to ask a question about page 6.
This one?
Yes. About this, the use of the Gauss theorem here. Please correct me if I'm wrong, but the integral over omega has all the times and all the temperatures inside it. I mean, it's an integral over the evolution of the fireball, yeah? And it also contains, so it contains the times that the temperature is not very high, and for example, it's around the critical temperature, and rho mu J mu is equal to 0 is not a good approximation. Yeah.
You mean that these derivatives of temperature, there is some region of space inside the Corgovan plasma which are high. Is what that
no, yes, this is also true because there are a lot of out of equilibrium things happening inside this omega. But also we have times that the temperature is not very high, but we are not still on the Fresnel surface.
Also here, the point is that the overall density operator is given by all the volume integral, and
yes,
also,
and
so even if there are some points where it's high, what you are interested in is the total operator is high or low, and overall this term expect to be small compared to this one. But also I think that currently there is no much, these dissipative terms are not being studied into much details. So it may be that some surprise can arise from these dissipative terms, and there might be a situation where dissipative terms are relevant or can bring a significant contribution. With this, I agree.
But let us forget about the first two terms in the integral, yeah? These are not our concern right now. But the last term.
Yes, the divergence
The
of
last term, yes, it's because you have times that you have regions here that this M is not, I mean, the quark's mass cannot be neglected in comparison to the temperature, and this guy is not going to be zero, yeah?
Yeah, okay, it also depends on how you define this axial current. For instance, the main reason this is not conserved is because of the axial anomaly and the presence of because quarks have mass, and therefore the axial current is not a conserved current even in for a classical theory. But the mass of the quarks, if you include in this axial current just the light flavors of quarks, then the value of the mass is small compared to the temperature, and so easily these are higher order corrections. And regarding the axial anomaly, you can always redefine the axial current by including the Chern-Simon term. This in a way will change the definition of the axial chemical potential, but in this case you can indeed write a current which also contains gluons, but is indeed a conserved quantity.
Thank you.
Okay, next question by Xu Guang.
Hi, Matteo, very interesting work. My question is about your density operator, also on this page 6. So it seems you choose the Balifetti symmetric T mu nu to define your density operator.
Yes.
I'm wondering, what if you choose not the symmetric T mu nu, but include the spin current also into your density operator? What would change to your result? I mean, or whether your result depends on how you choose your density operator according to different pseudo gauge?
Yes, as far as I understand this problem is that if you want to think about local thermodynamic equilibrium as close to global thermal equilibrium, then you see that naturally the symmetric stress energy tensor arise from defining the global thermodynamic equilibrium. Therefore, this is an indication that you should use the symmetric stress energy tensor. And then what you can, the pseudo gauge that you can do is by inserting, for instance, the spin part. And in this case, it's not clear that if you could do that, and if you require an additional hydrodynamic parameter, which would be a spin chemical potential. But as for now, we don't have any indication or any reason to think that the quark gluon plasma is generated with a spin axial chemical potential. But we have reason to believe that the quark gluon plasma is being generated with an axial imbalance. Therefore, it is perfectly fine to consider this term, but it is more speculative and more to add other additional spin chemical potential or other things that we don't have any solid evidence. And also the effect of spin of pseudo gauge transformation in the stress energy tensor is again something that is not been investigated at full, and therefore it's still an open problem if different choice of stress energy tensor and other quantities can indeed affect thermal averages or hydrodynamics.
Yes.
So I can
Yes.
be sure on what the final conclusion is.
Oh, yes. On the other hand, this JA mu that you introduced in your density operator is
Yes.
the actual current, right?
Yes.
And we know that the actual current is somehow like the spin current.
Yes. Yes. Yeah,
contracted with the Levi-Civita operator. So would this means that this zeta A, that your actual chemical potential actually plays some role as the spin potential or spin chemical potential?
Yes, but due to the quantum nature of fields, essentially you have a lot of degrees of freedom. Therefore, I think you can, if you find any conserved quantities, you can always add here in the density operator some constraints of conserved quantities, and you can include them. And even if the, for example, for Dirac fermion, the axial current is related to the canonical spin tensor by just the biduality transformation. I think you can think of a situation where you include two different chemical potential, one from axial current, one from this spin tensor, and obtain different things. But what you are doing is including other hydrodynamics fields, other effective parameters to describe your hydrodynamics or your evolution. And as I told you before, as now you don't have any reason to include this spin axial chemical potential. If in future we have evidence to say, okay, the Corcoran plasma is produced with this, we require this additional hydrodynamic parameter, then you can include this in the density operator and see what changes and how it affects polarization.
Yeah.
But
yes,
for now, I don't see any.
Sorry, Chairman. Dirk.
Yeah.
Can I comment?
Yeah. Is this your question or is this the comment?
No, I mean I wanted to make a comment, but this is related to what Shugong said.
I have it on my list for the roundtable discussion. I don't know. Do you want to?
No. I just wanted to say that this is related to question by Shugong that so it is true that in the Dirac field, in the Dirac theory, J mu, the axial current is the dual of the spin tensor.
Yes.
But in this case, the contraction is different. So J axial current is contracted directly with d sigma mu, which means that you are considering the, say, in the usual phrasing, you are considering the time component. Therefore, it is qualitatively and quantitatively different from the. It's also qualitatively different from say a contraction of the spin tensor with the spin potential. Okay, thank you.
I see.
Yeah, very good.
You can expect from a spin tensor something more similarly to the thermal vorticity than to this axial current.
Yeah, thank you.
Okay, maybe Gao Jing is the next.
Hi, Matteo. Thank you for your talk. Can you hear me?
Yes, clearly.
Oh, actually, I'm just, of course, it's a nice work. I'm wondering if you can detect such effect through the polarization of lambda particle. Because for lambda particle, you will get a feed down from the decay or Xi. It's weak decay, right? So then it will just give the same spin structure like you give out. That is proportional to the momentum, right? Do you
Yes,
think?
yeah.
So I'm wondering. So
it's exactly
if you
look for
search for other particle.
Sorry, can you say the last part again?
I mean, for lambda particle, it seems impossible to detect the axial anomaly effect because it will feel down. It will get some feed down from the weak decay or quasi particles. So then, do you need? I mean, do you search for other effect? So search for such effect from other particles polarization. Okay. Do you understand? Yeah.
Not clear. Maybe I can say to you that what we are proposing is, for instance, to what we can do is what we can do in a measure in an experiment is essentially to identify an helicity of the lambda and anti-lambda particles, because they are they decay with weak interaction. Therefore, there is a correlation between the daughter and their original spin, and therefore you can also reconstruct the helicity of the lambda particles. And what we propose is here is not the conclusive answer, or we are not clean. This is the best observable that we can use to look for this local parity violation. But what we want to say is that this measurement of polarization and helicity on emitted particles are feasible, and maybe we can use some observable like this, and then since this, then we haven't make any simulation or any very accurate prediction on how these correlators should give. Also because we don't know the value of the axial imbalance, because there is a large theoretical uncertainties on how large it is. Therefore, this is just the proposal, let's say, of an idea on how to we can discern this effect from what you expect from thermal vorticity. So I don't know what maybe the feed down effect can maybe can or maybe cannot decrease the signal, but for now I don't know.
Okay. I also have see Oleg has a question. Huh?
Okay, thanks. Actually, I have a related question. Indeed, yes. As helicity can be revealed only, helicity and polarization is revealed in weak decays. And finally, the observable should lead to some momentum correlations. And, yes. And there are some specific p-odd momentum correlations, so-called handedness, which appears in jets, and also we looked in models in heavy ion collision. So my question is, maybe it's possible to go one step further and just look for handedness, for p-odd correlations of momenta.
Well, maybe if you have a correlation between momenta, for instance, in this slide here, you can insert all the correlation between the particle, if you know how to describe them, and see what this correlator turns out to be. And if you have an idea how to rearrange all these quantities to use handedness to have a better observable, you're welcome to propose it.
No, what I mean that if you have some azimuthal modulations of helicity after decay, convoluting it with decays asymmetry, you come inevitably to to correlation of momenta. So just it's hidden in your result. So I don't know how, maybe it's too difficult to calculate this, but I suspect that final observable one step further for the just helicity modulation would be momentum correlations. I don't know which one. So also maybe here when you show this. So maybe this somehow should be revealed also. We looked for simple cases of handedness, but it can be different way to construct the p-odd correlations of momenta. Because finally what is measured are momenta. Only it was a question in the first day, right? When polarization can be measured? Only from momenta, right?
Okay, if this is a concern, we can check if if this correlation momenta can destroy or not this correlation between the two helicity.
So I see, Francesco, do you want to put your comment right to Alex's question now, or?
Okay, I can do it. I mean, of course you cannot measure helicity of the lambda directly. What you do is you measure the direction of the proton, or the momentum of the proton in the lambda rest frame.
Yeah.
Okay, eventually this is what you measure. You measure this, and then you relate this, the scalar product of the proton momentum in the rest frame of the lambda with the momentum of the lambda at different azimuthal angles. This is the usual way of measuring polarization of the lambda.
Yeah, so I think that finally, if you convolute your equation with distribution, it should lead to some kind of handedness. So I'm not.
Of course, eventually you measure only momenta. Yeah.
Yeah, exactly. And for in the momenta, there are some different terms on momenta dependence, and handedness is just p-odd contribution to just momenta dependence. So this is just, I'm not objecting. I'm just it's complementary. Just. Aspect of your work, I guess. Yeah.
Okay, maybe last question by Jinfang.
Hi, Matteo, so very interesting talk, and also I think the idea itself is very interesting. Can you go back to 18, one slide back? Maybe one more. Yeah. So here I just want to be sure that I understand this plot. So you're putting the number like P0, P1, S0, S1 just for illustration, right?
Yes, just for
these numbers are not, what I mean is that suppose I'm an experimentalist, I want to go ahead and measure it, but these numbers are not exactly what you would estimate, right?
Yeah, exactly. These, as you point out, these are just to illustrate the parity transformation, the difference in the scalar part and pseudoscalar part.
So do you have an idea or have tried to estimate how large those coefficients could be? Let's say on order of magnitude level.
You can use this formula to evaluate the helicity induced by the axial current. And one can use, for instance, your models, and then at the end of the freeze out, use this formula. Similarly, on how you use the formula for thermal vorticity, you need a hydrodynamic simulation to know how large the thermal vorticity is along the freeze out hypersurface. And if you use an anomalous hydrodynamics which contain anomaly and this axial charge, then you are able to also to give a prediction. But of course, here we open many other problems. For instance, how to give the initial condition of the axial current, of this axial current, of the axial imbalance that you have just started to study and propose.
Roughly, it looks like it's basically proportional to the axial charge at freeze out, or average axial charge at freeze out.
It's the average of the zeta A over the freeze out surface, no?
Yeah, also depends on the how this axial zeta A, the ratio between axial chemical potential temperature, depends on coordinates over.
Sure. No, I appreciate that, but I think for motivating, let's say, experimentalists to look at it, it would certainly be useful to have some sort of order of estimate, magnitude estimate? Because I understand that to precisely predict it is not easy, but some sort of say, are we expecting 10 to the minus 1 or 10 to the minus 2, kind of thing.
A very rough estimate is given by this simple formula here. If you consider it decay constant and everything, then this the density induced by axial chemical potential is this factor zeta A divided by 2, and GH is the axial charge of the baryon species, which is deriving from the matrix element between the ingoing.
I see. So this,
you can use these to have an estimate on how large is this effect.
Okay.
thank you.
Francesco, I see you have raised your hand again, but
yeah, I mean,
we have to move on.
Very quick comment to Jingfeng. I think Jingfeng, I mean, you have a code, right? It's an anisotropic viscous fluid dynamics.
Yes, for the AVFD, yes.
Oh, sorry, anisotropic, axial.
Anomalous.
So I think that
anomalous, yeah.
Anomalous, sorry. That I think in principle you can calculate this, and then we can use the axial charge or the axial chemical potential freeze out to calculate the helicity pattern and the coefficients S and P.
So do we know all the numbers for this G of H? Perhaps not all the hadron, I guess.
Is this the axial form? Is this the axial coupling constant? And it's on the order of 1, right?
Yes, the axial current can be either negative or positive, depending on the. This depends on the flavor transformation properties of the axial. So it depends whether, I mean, it is a flavor singlet or flavor octet or a combination thereof. And then you have different axial charges.
Okay. Very good.
I think that'll be interesting to try.
Yeah. Then let's thank Matteo again.